Metamorphic rocks are formed as a result of changes in the mineralogy and physical structure of pre-existing rocks by natural processes such as the introduction of heat, pressure, and chemically active fluids without melting into magma. This change happens due to the fact that each mineral has a range of specific conditions at which it's stable, and any shift in these conditions leads to the formation of another more stable mineral. Metamorphic rocks mostly occur in continental shields and orogenic belts where they are exposed at the surface, indicating extensive uplift and erosional processes, and they are also found overlain by Phanerozoic sedimentary sequences in continental platforms. Depending on the geologic setting or tectonic environment, there are several types of metamorphism, and here they are. Number one, contact metamorphism, which is when an igneous body intrudes and backs adjacent rocks. Another similar type is hydrothermal metamorphism, or metasomatism, happens when aqueous fluids move through large areas of rocks, supplying heat and chemically active ions that cause recrystallization. Number two, regional metamorphism, where the intense heat and pressure associated with colliding continents metamorphose the rocks nearby. Number three, burial metamorphism. This is associated with very thick sedimentary strata in a subsiding basin. Number four, subduction zone metamorphism, when sediments and oceanic crust are subducted fast enough that pressure increases before temperature. Number five, metamorphism along fault zones, which occurs at depth and high temperatures, causing pre-existing minerals to deform by ductile flow, resulting in the formation of rocks like mylanites. Number six, impact metamorphism, and this takes place when meteorites strike the Earth's surface, producing fused, fragmented rocks rich in glass similar to volcanic bombs called impactites. Metamorphic grade is largely determined by the intensity of temperature and pressure, which generally increase with depth. Relative position of the rocks experiencing metamorphism, in addition to the time factor for such processes, take super long periods of time and probably more than one episode of metamorphism, reflecting the interplay of tectonic activity and magmatism. Geologists classify metamorphic rocks into facies, which are groups of minerals that form over certain ranges of temperature and pressure conditions. For instance, sodium amphibole glaucophane is only formed in low temperature and high pressure, which are conditions almost exclusively found in subduction zones. So it's reasonable to assume that any glaucophane containing rock must have formed there. This is how geologists use metamorphic facies. Rock X contains minerals A, B, and C, therefore it must have formed in environment Z. Metamorphic grade can also be examined by the degree of recrystallization or foliation, and this is illustrated by the progressive changes in texture as the metamorphic grade increases from low to high, such as slate, phyllite, schist, and gneiss. The highest grade of metamorphism is represented by migmatites, which are rocks that have been partially melted, and after this stage, the rocks turn into a complete melt, therefore entering the igneous realm. Metamorphic ore deposits are formed during the process of metamorphism and can be classified into various types based on their geological characteristics, mineralogy, and economic significance. Some common types of metamorphic ore deposits include: number one is skarn deposits, which form at the contact between an intrusive igneous rock and a carbonate-rich host rock like limestone and dolomite. Skarns can contain a wide range of ore minerals like iron, copper, zinc, tungsten, molybdenum, and others. Number two, metamorphic hosted ore deposits. These are deposits that are formed directly within metamorphic rocks without any associated intrusion or hydrothermal fluids. Examples include metamorphic hosted gold deposits, metamorphic hosted graphite deposits, and metamorphic hosted manganese deposits. Number three, metamorphic exhalative deposits, which form from the deposition of ore minerals from hydrothermal fluids that are exhaled from the rock during metamorphism. Such fluids can deposit ore minerals like lead, zinc, copper, and silver in fractures, faults, and other openings in the rock, leading to the formation of ore deposits. Number four, metamorphic metasomatic deposits, and these are ore deposits that form through the exchange of elements between the rock and the fluids during metamorphism. Ore deposits like those of iron, copper, and zinc can form this way. Number five, marble-hosted ore deposits, which are formed from the recrystallization of limestone or dolomite. Marble deposits can also contain high concentrations of certain elements such as magnesium, lead, zinc, and copper, which can be extracted economically as ore minerals. These are just few examples of different types of metamorphic ore deposits.